Changing the equilibrium, changing the volume. Here we're going to talk about a system that's supposedly already in equilibrium. We're going to look at this system, SO2, sulfur dioxide plus oxygen forms sulfur trioxide. There should be two of those there, sorry. That's balanced properly. Anyways, and we're going to imagine how this equilibrium is going to shift if you increase the volume of the container. So in our equilibrium situation, we're going to have some SO2s, some O2s, some SO3s. And this equilibrium is going to be dynamic. So that means every once in a while, some of these SO2s are going to bang into an O2, and then they're going to collide and reproduce some SO3s. And similarly, some of these SO3s are going to combine with each other and bang into each other and come back out as SO2s and an O2. So it's a dynamic equilibrium. They're shifting in and out, and the two reactions continue, but the reactions are occurring at the same rate, so we don't notice any change to the macroscopic populations of any of the particles. Okay, now let's imagine that this is all in a container, and we take somehow these sidewalls and we increase the size of the container. So we make it even bigger. Now with our reaction here, what we have to assume when we make our container bigger is that there's going to be less collisions between particles. So what that means is as we increase the volume of the container, both reactions will slow down. So we're looking to try and figure out which reaction is going to slow down more. If we look at this reaction, the forward reaction, we can see that three particles need to come together in a collision to cause the collision. So making the container bigger is going to cause a huge decrease in that collision rate. Because we have to get three things into the same location at a time, making the container bigger is going to make that even more unlikely. Alternatively, with this collision, we only need two particles to come together to form the collision that could result in a reaction. What that means is, although both reactions show less collisions, the decrease in collision rate will be more evident with the forward reaction than the backwards reaction. As a result, the forward reaction will slow more than the backward reaction. So the forward reaction has a three-particle collision. The backward reaction has only two particles colliding. So if I increase container size, three-particle collisions will become much less likely. Two-particle collisions will become somewhat less likely. They'll reduce, but not as much as the three-particle collisions. What that means then is that this reaction rate is going to slow a lot, and this reaction rate is going to slow, but not as much. So if we consider our equilibrium, SO2 plus O2, two of them, going to SO3, two of them, this reaction rate will slow, and this reaction rate will slow too. I'm going to put that on the bottom so it's lined up with the original arrow. There we go. So the forward reaction is going to slow right down because it requires three particles. It becomes very unlikely. The backwards reaction is also going to slow, but not as much. Now what we can see is that the backwards reaction is now favored. That means that the equilibrium will shift towards the side with more particles. Basically, the more particles required for the collision, the more that increasing the volume will decrease that reaction rate, and so the equilibrium will shift to produce those things to up that reaction rate and get them back even to each other. From a Le Chatelier perspective, if we think about changing the volume, we should think about the effect that will have on changing the pressure. Specifically, if I increase the volume of the container, since there's more surface area for the particles to bang into on the side, I'm inherently reducing the pressure. The system then is going to try and respond in such a way that will increase the pressure back up. How can you increase the pressure of this gas? By producing more gas particles, or by tending towards the side that has more moles of gas on it. So Le Chatelier says the system will attempt to counteract any change that's made in the system. So if you increase the volume, you decrease the pressure. So the system wants to increase that pressure back up. It'll do that by making more gas molecules. What's really going on? Well, whoever requires more particles for the collision gets slowed down more, and so the other reaction becomes favored and the equilibrium shifts. If I were to imagine my populations of SO3, SO2, and O2 having become stable at some equilibrium value, and then the pressure or the volume is increased, since I have 3 particles on this side and 2 particles on this side, the increase in volume decreases the pressure, so the system tries to recreate more pressure by shifting to the side with more particles, causing more O2 to be produced and more SO2 to be produced, and using up some of our SO3 until a new equilibrium is reached, where, despite the fact that these collisions have become less likely, the concentration of those species has been increased to the point where it is where that reaction rate becomes equal to the backwards reaction rate again. We can do the same thing for decreasing the size of the container. Let's take a different reaction this time. Let's take 2A reacting to form the compound A2. And let's take our container and let's squeeze it in so it's very small now. What that means then is that collisions between the two A particles will become more likely. That means that this reaction rate, the forward reaction rate, will increase. Since A2 doesn't have to run into anybody else to decompose into two A's, the backwards reaction rate won't actually be changed by the decrease in volume. So, since these guys are colliding more and these guys don't need to collide, the smaller container makes this reaction rate go faster, and as a result, more A2 will be produced. Again, if I imagine my two populations, I have A and my A2s, and they're at some sort of equilibrium value, and then I decrease the size of the container, more collisions of A will cause it to be used up, and that population will decrease, and more collisions of A2 will happen, causing that population to increase. Le Chatelier would say the decrease in volume causes an increase in pressure, the system would respond in a way so as to undo any change that's applied to the system. So if I have an increase in pressure, the system wants to relieve that pressure or decrease the pressure. And so it can do that by going from many gas particles to few. And so the system can respond to the increase in pressure by making less particles to lower the pressure. So the proper way to think about this, to understand why it's happening, is to consider the likelihood of collisions between particles. The more particles, the more the size of the container will affect the number of collisions that's happening. We're talking about gas particles here. Other types of particles aren't as critical. However, Le Chatelier tells us, if we want to think about this and just get the answer right without totally thinking through what's happening with the collisions, we can just imagine the pressure. If we increase a volume, we decrease a pressure, so the system has to tend towards the side with more particles to refill up that pressure. Or if we decrease the volume, we increase the pressure. So to relieve that increase in pressure, we're going to tend towards the side with less particles. So whether we're considering the collisions or the Le Chatelier point, we get back to when we increase volume, the system will tend towards the side with more particles. And when we decrease volume, the system will tend towards the side with less particles.